Okay, so I'm going to start my personal timer because this talk is a bit of a speed run. Basically, hold onto your butts and strap in because we are going to cover about 3 talks worth of content in 45 to 50 minutes. The slides are online, the talk is being recorded. All major source code will be available online, so please don't feel like you need to take lots of notes. And let's just get on and do some crimes. So first of all, we're doing a talk, so I need to do some introductions. Hello, my name is Kiera Lord. I go by Cratesmith online most of the time. I'm a programmer at 5 Live Studios. Here is the list of things that I worked on. Basically, this is just an indication that I'm old. The most recent thing I made was Windbound with 5 Lives. Some things that are obvious as fuck that we can't go on without saying. First of all, I'm going to swear a lot through this talk. Trans rights are human rights, sovereignty was never ceded, Black Lives Matter, free the fucking refugees, fuck Murdoch, kink belongs in pride and cops don't, be gay, do crime, let's do some crime. So let's talk a bit about what this talk is. First of all, this is a sequence of how I build certain things in generics. All of these things are things where I've shipped real games with them. So this is not untested, crazy faffing around boost level stuff. This is actually working. And we're going to start off simple and we're going to work up our way up to very complicated things. What this talk isn't, it's not a Stack Overflow post. This shits me to tears. Someone asks a question on Stack Overflow and they'll be like, I have this really specific edge case problem. The first answer is, you shouldn't do that, that's bad. Fuck those people. If you have a reason for going into an edge case like we're about to, you're an intelligent person, you've got a good reason. All right, so what I'm hoping you're gonna get from this talk, I don't really mind if you're not able to follow in every single step or concept or example. I really wanna just show my process and philosophy for working with complex generics, and I'm hoping that in doing so, you'll pick up enough of that and be able to build your own way of doing it, because everyone's different and this is quite a personal approach for me. So before we start, we have another primer. We're just going to quickly go through what are generics and a couple of required knowledge before we really get into the meat and potatoes. The first one is what are generics? And generics are just basically mad-libbed code templates. It's a block of code, a class or a method where parts are missing and they get filled in by the compiler, and every single time you use them in a different way, it will generate a new variant of that class at compile time. You've probably seen them, used them in lists, singletons if you're in Unity. You can't use C# without doing it. Basically, the less than, greater than parameters, that's generics. And yeah, the most important point is that when the program is compiled, all the used variants of generic things get built into unique specially typed versions. So, and then you have the where keyword, which is the other part of generics. So generics are defined by the parameters that they take. All of the parameters are always types in C#, but by default, you will have a generic, you could take anything you wanted, but then you can't do anything with it because it could be anything. And so the generic constraint, type constraint, which is the where keyword, allows you to say this thing will be a struct, this thing will be a subclass of this class, or this thing will have this interface. Anytime you constrain one of these parameters, you can then use the features of that. So if you say it's a struct, it suddenly can't be set to null, or if you say it can be constructed, you can suddenly call new on it. We will be using this a lot, so watch for them. And most importantly, when do you not want to use generics? Always. Funny thing for me to say in this talk, but most of the time generics are the wrong solution to a problem. They are hard to maintain, they are complicated. Adding extra parameters to a generic function can be an absolute nightmare. So if you can do it without generics, do it without generics. The better question is, when do you want to use generics? There's a couple of cases. The most common one is to avoid boilerplate or copy-paste code. The second one, which is basically going to be the next 2 points, is basically if you want to avoid boxing with structs in common cases. So basically, if you're using an unknown struct type and you need to be able to avoid that thing going onto the heap, or if you're enumerating an unknown container and you don't want to go to hell. We're going to show you how that works soon. And then finally, if you've got a very specific kind of API you want in, and you can't really build it otherwise. All right, so what is boxing and why should you be scared? Primer, there are two types of memory that are like main memories in C#. You have the stack and you have the heap. What's the stack? The stack is basically where your local variables and your current function are being held. It's a pre-allocated block of memory. It's all there. It's cache friendly. It's super fast. Basically, it can only store the data that is value types, numbers, structs, enums. And only the stuff that will exist within this current function or like basically can be passed out as a return type. The heap is where everything else lives. And the heap is basically free allocatable memory. Reference types, so anything that's nullable, classes, interface variables, always live in the heap. Now, the heap isn't bad per se, but allocating and deallocating memory from it is an extra time cost. And accessing in the heap is often not cache friendly. It can be depending on use, but it's not guaranteed. So the heap isn't a bad thing on its own, but we don't want to unnecessarily use it. So what is boxing and why is it unnecessarily using the heap? Well, if we could do any of these things, we box them. If we go and take, basically, if we take a parameter that is not nullable, struct, value type, etc., and we go and put it into something that is nullable, so we put the number 3 into an object variable, or we pass a structure, like toString takes an object as its parameter, and if we pass in a structure to that, or if we return like a struct enumerator out of as an interface, all of these things are passing them to reference types. So you think, oh, maybe the language does something really clever with this. No, it doesn't. What it does instead is it invisibly allocates a box of memory onto the stack, copies your value into it, and then points the variable or return type to that box. It's just invisibly allocated memory, probably where you didn't want it to. So yeah, this makes lots and lots of tiny mini allocations that fragment your memory and tear apart your performance. And it's really good at doing these without you knowing. So I highly recommend you use an IDE like Visual Studio with a plugin or Rider that can highlight when it's allocating memory in your code. All right, so we've covered the basics. 7 minutes down, let's do some crimes. I guess the first thing we're going to do is we're going to make enumerators work for us. There are some major problems with working with unknown collection types, and we're about to go through that. And quite rightly, a lot of you are like, hang on, what's wrong with collections? I've used these all the time. Well, can anyone spot the boxing allocation in this function? I couldn't. This one really threw me. So this is just a function here where we're finding the first item. We're really just going through, we have an IEnumerable, which is basically an unknown collection we're passing in by an interface. And we're looping through until we find one that matches the first parameter, like has a member that matches the first parameter. So it's basically find first thing that matches. It's the fucking for each. Like, I could hear somebody here knows about this. All right, so what for each actually is, it's kind of a shorthand for give me a hidden local member that is the enumerator, call get enumerator, and then while move next on that enumerator. Now it's a bit weird, like where's the boxing in this? The boxing is the get enumerator. And the reason this is happening is because we got this struct enumerator here. To avoid allocating memory every time you call for each, most collections and most sane collections will use a struct for their enumerator, because structs always live on the stack. So when you normally call for each, sorry, I've gone too far. When you normally call for each, it calls get enumerator, it has a struct enumerator, it doesn't allocate any memory. The problem is we're accessing this by the IEnumerable interface. We don't have access to that method which provides the enumerator as a struct. We get given it as IEnumerator T, which is an interface. So on the way to us, it gets boxed. Simply because we're calling the wrong version of the function. So we're fucked. We can't use enumerators at all. Well, that's how it looks, hey, but there's a catch. You see, C-sharp devs even patched for each to avoid this problem, because originally for each required that you use, like, it would look for I enumerator or I enumerator T. So instead, they added duck typing to the language explicitly for the words get enumerator. Basically, that first get enumerator, the public, it doesn't actually look at the type and look up, oh, this is an IEnumerable interface, call IEnumerable dot get enumerator. It looks to see if there's just any function called get enumerator. You can call, as long as there's a function called get enumerator on something, you can for each it, which is really cool. It helps us with structs later on, but also it means that by default, for each will avoid boxing on its own. But because we're working in generics where we only know the interfaces, that's not really going to work for us. So we need to find a way to work like this. So yeah, this only helps us if we know that specific get enumerator method. And so if we're in generics, we're in a context where we only know the interface. And well, that means there's no way to call the right get enumerator, because that only we can only get that if we have like list T, hash set T, etc., etc. So we're fucked, right? Nah, we can get around that. All right, so the first step here is that we don't really need the container. We're going to take the enumerator itself as a generic parameter. So what we do is we replace our functions parameter, which was the container, as an IEnumerable interface, and we just take a generic parameter where that parameter is IEnumerator of our item type. And then we do the while move next thing ourselves. And then when we call it, we just call it with find first item of type, and then we pass in item list.getEnumerator. And I'm sure some of you who haven't played with this before are like, hang on, you just used an interface. Like, we're going to box this, right? Nope, that's a type constraint. When we actually build this function, what happens is we get this. Basically, this is the variant it's generated of this method. So find first item of type uptick 1. So it'll generate like uptick 2, 3, 4 for every single variant it creates. And it's actually gone and ad-libbed in the exact type of the enumerator. This method will not box. It's using the struct properly all the way through. So, the only downside to this is that working with enumerators is a bit more of a pain than working with the containers. We don't know how many items are in the collection. We can only iterate through them in the order that the enumerator does it for us. So if we wanted to go through this list in reverse, it'd be a right pain. And then we also need to take the enumerator as a generic parameter. Extra generic parameters are can always be risky. But this is a double-edged sword. We can get up to all kinds of bullshit with this. We don't have to pass in the default enumerator for our collection. We can go and make our own. We could go and make struct enumerators that do all kinds of shit, like wrap other struct enumerators and iterate them, I don't know, selectively, change the result, etc., etc. We are going to get to that crime spree later. There's a couple of other things that we need to sort of cover first. But that's a nice way of having a function that enumerates any method you want without having boxing. It's a really nice one to know. Secondly, enums. I love enums. They're way cooler than you might think, but they're kind of fucked, so let's go and fix that. Oh, by the way, there's like little source links here. They are, hang on. Let me just work backwards. There we are. These source links, there'll be one at the end as well, so don't feel like you need to panic and write that down. So, enums are strongly typed numbers. They can be implemented as any 8 to 64-bit integer type, signed or unsigned. And so you can specify what size you want for them. And so basically you can have your player IDs and your network client IDs and have them like the compiler will defend you ever accidentally trying to cross these with other numbers. So that's really nice. Just native strong type numbers is fantastic. Named constants, that's how everyone's already used them. They also do bit flags. If you add the flags attribute, you can then start using binary operators with them. And they're natively implemented in just about every editor under the sun. So great. Well, what sucks? Well, The API, system.enum, I think it hasn't been updated since C# 1.0. Every single method in there takes object, like a parameter as an object. Everything is boxed, everything allocates memory. People avoid using enums because everything about them kind of is a bit rubbish. So there's no good way, and then secondly, the one that affects us a lot is there's no good way to convert between generic parameters that are enums to and from their numeric types. Now, this is actually something that should work, but there's some problems with the way that they've implemented generics around this. And so we need to make our own custom way to get around that, because if we're working a lot in generics, we're going to need to be able to use the enums within generics. So this is a bit of this is part of the process part of the talk. So as our first step, we're not just going to dive in and just fix enums. We're going to look at what are we really after here? Well, the main thing we want is we want to replace system.enum methods with a pre-calculated lookup table. It has to be auto-initialized before the first use, and we also need those generic uint to 64 enum conversions and other helper methods for things like get name, does this thing have a name, etc., etc. All right, so first of all, let's do that static lookup table. Bam. It was really easy. We just need a static class that is generic based on the type of enum. So enum info t, where t is an enum, this is a static class, and it has a static constructor. Static constructors are really cool. They're guaranteed to be called before you use this thing for the first time. So before we access any of its variables, it will have called this and filled them out from using the gross ugly system.enum methods. So we'll have our list of names from get names, list of values from get values. We'll have the underlying type. And remember, each variant of enum info is a unique class. So each of these static lists is unique to the type of enum you're using it with. All right, so next up we need to design those helper methods we need. The way I like to do this is I like to build a unit test that has the methods before they exist. I just write out the API I want, and then I work backwards and build that API, and then I get it so the test actually runs and passes. So in this case, I need the to and from number versions, so I'm going to do just a test with a short. In my code, I do lots of types, but had to pick something. So basically start with the number 4, convert, and then we have as enum, enuminfo.asenum to convert that to some kind of short enum, and then take that and convert it back using a function called as_uint64. Now, the reason I pick uint64 is rather than having lots of conversion functions, remember enums can be any number from 8 to 64-bit. Well, that means we can always safely cast them out as 64-bit, so it's basically, that's always the output, keeps the API a bit smaller. So yeah, then I just do a test to make sure that one's working. And then also I define a hasName function. I just make sure that a already existing name one will work. And then also, rather than using toString, which allocates memory and is broken in a lot of ways, we will just like have an asName function in enuminfo. All right, so let's go and build those. So as enum, it's pretty simple. You notice that I've created an extra static class up there, which is not, I appreciate this is really tiny text, but at the same time, remember, all of the source code is available. I'm really just trying to use these as an example. The static class that I've got at the top is there as the interface. I don't want people having to say enum info of this type every single time they're going to call a method. There's a lot of shortcuts we can do by putting like helper accessor methods in a non-generic class. Secondly, we then have it just points us to our real as enum function. And this is just a switch statement. We're just doing a size of t on whatever your enum type is. And then using unsafe utility, or if you're not using Unity, you just use unsafe.as to hardcast the type to the enum type. There's an even faster way to do this if you want to emit this, but I wanted to make sure my code was ahead of time compatible. There's other options here too, but anyway, so as enum works like this, and as uint64 is exactly the same, just in reverse. The syntax is slightly different because I don't need to create extra variables in there, so I can just use the switch expression syntax. I personally like it. You don't have to, but that's what that is. It's basically just doing the same thing in reverse. We are hardcasting from type t back to whatever it is based off how big your your enum type is. Okay, so then we get to the one that's a little bit different. We've got asName and hasName. So we've got the two helper methods up here. They actually do the work, and then we have try-get-index. Basically, let's just talk about try-get-index first. Something about enum, the enum methods. System enum.getValues returns all of the values of defined values in your enum in unsigned integer order. So it converts them to uint64s and then it sorts them. And then the names come out in the same order. So what we're interested in for the names is we need to find the index of the value you're passing in. First of all, most enums have undefined numbers, and in which case their numbers match up with their index. So we always first just check, hey, if we use the numeric value of the enum as index, is that the right value? After that, because it's sorted, we can binary search it. And then, so we know the index of the value we want, or we know it doesn't have an index. We can then say, all right, hasName is just check if it has an index. If it has an index, it has a name. And asName, we basically do the same thing. Does it get the index of this thing? If it does have a name, if it does have an index, look up that index in the names list that we built in the static constructor. Otherwise, just return the text unknown. All right, sorry, I know I'm going a million miles an hour. Just remember, all source code is online. But before we go any further, we need to have that talk. So generics is all fun and games so far, but now we need to talk about inferred generic method parameters. So let's compare these two examples, because right now these aren't too scary. But you see how asEnum requires us to define, like, in less than, greater than brackets, short enum, but asuint64 doesn't. The weird thing here is that both of them have exactly the same generic parameter argument. They both take t where t is a struct enum. So what gives? Like, why is one special? Well, basically, you can omit the generic parameter arguments if all generic parameter arguments are present as method arguments. This only works for methods, you can't do it for classes. So basically, in the example below, you got my method 1, and it's got 3 generic parameter arguments, but only the first 2 are supplied as method arguments. You would need to specify all 3 generic arguments as well as the whatever values you're putting in for the method parameters. Oh, sorry, yep. The second one will work because every single generic argument is present there, and it's very bad at picking them out of generics and stuff like that. So yeah, you usually have to use the exact type. So in this case, asuint64 works because it takes t as its only argument, which means it can infer t from that. So this is something you should do all the time. Having people explicitly mention, like specify generic parameters is really bad unless it's something like enuminfo.toEnum, and then you need to say what kind of enum you want. Or like in Unity, gameObject.getComponent, and the generic parameter is which component you want. Anything that has extra redundancy in it or requires people to specify lots of parameters that they'd have to go into detective work for. So like in this case, if I had to redundantly say asuint64 short enum, and then again, I'm just passing in a short enum value, that would be bad. And you just know, if it feels wrong, it is wrong. So this is cool, it's just a shorthand, right? Well, no, this comes in really handy later, but as a first thing, it's just going to be quite helpful when we start using these things as extension methods. So for our API, we really want to get away from having to type enuminfo so much. So rather than writing enuminfo.asEnum, we really want to write like mynumber.asEnum, or like my enum as uint64, that sort of thing. Like just as if they were member variables. And C# kind of has a way of doing this. You slap the this keyword on the first parameter, and what it does is rather than calling them, you have a second option of calling it as if it was a member of something else. Basically, anything that matches your first parameter. Now, the caveat to this is this only works for static methods that belong to a static class that is not a generic static class. But these can be generic methods. So when you do this, you have 2 different ways of calling the function. You can call it as the member syntax. So here we have our add1 function. It's a public static int, takes a this int self, like self is just the parameter name. And then I can go debug.log 3.add1, or I can go debug.log example extensions.add1 3. Basically, the first parameter is being taken from the left side of the dot. Those two calls are exactly the same. It's just compile syntax. This thing is really useful. So generics do work with it just the same. You can create a generic extension method. The advantage with generics is extension methods only work when the parameter type matches the first parameter type is whatever's on the left-hand side. With generics, you can define these things where they'll work on all kinds of structs. Or like, basically this is count string. It will work on any kind of T where T is an I collection. So this just returns a string based off the number of items. We can call it on list or hash set and it works just fine. What's even better is this will work on structs without boxing them, whereas if you pass them in as interfaces, it would box them as we saw before. All right, cool. We're at 26 methods. I need to speed up a bit. We just convert all our existing methods to extension methods that were already in a non-generic static class. So we just slap the this keyword in. So asenum gets a this, asun64 gets a this, and all of a sudden we can just use these as like 3.asenum and then the enum type. All right, so that may have seemed like a little bit an anticlimactic end, but that was a lot of really required stuff for the crazy bullshit we're about to get into. We are going to fix link. Okay, now I appreciate link is very good at editor time. It's really useful. It's a nice query syntax, but if it's in your game code, oh God, is it ripping your performance to shreds. What we're building here is not something you should use a lot. It's something where you can go through and you can replace link with it. And it's relatively close to the same syntax, but it doesn't allocate memory. So what is link and how does it work? Well, link is this the syntax of like mylist.where and mylist.select. And you pass in functions to it. So like I've got a list of the numbers 0, 1, 2, and 3. And then I say, okay, I want the numbers, all the numbers that are greater than 1, and then all of those numbers, I want to add 1 to them. And then I want to loop through those. So it's a really handy way to do complex, like nested loop logic. So how does this work? Well, if you've followed along really well, you'll get you get uncomfortable now. Each one of these is a generic extension method, so where and select, that take an IEnumerable T as its this parameter, so the interface type IEnumerable of T, where T is the item, and it will return a custom IEnumerable that performs the operation. So IEnumerable T, where like if it was of int, it would be IEnumerable of int is the type that it'll be using. So what's wrong with this? Well, this is the stub for the where query function. You can probably spot 2 of the problems already. So there are the 3 problems really. The first one, as we covered in the first section of this talk, this thing is going to box the enumerator. It has absolutely no way of not boxing the enumerator. It is taking a collection in as an interface. And it will be, well, strictly speaking, they do have some hard-coded outs. Link will not box an lists enumerator or an arrays enumerator under most circumstances. That's an aside though. It will return an IEnumerable as an interface. If that's a struct, it's getting boxed. If it's not, it's a new allocation. And finally, the predicate will always be a closure, and we'll cover what that is and why that is bad and how we can get around it in a second. All right, 10 minutes to go. All right, this is going to have to be a bit brutal. So as before, this is the first section of the talk over again. We need to go and change this method so that instead of taking an IEnumerable, it takes a generic enumerator as a parameter. So rather than having where take IEnumerable, we simply change it to have where take T enumerator. So T enumerator is our generic enumerator type, which is always going to be an IEnumerator of T source. T source is our item type, and it is also always going to be a struct. So we just guarantee that we're not being passed in any non-struct enumerators. I have just been told I have 10 minutes left. Let's rock. Secondly, it is returning IEnumerable, the interface IEnumerable. We do not want this. What we want to do is we have an IEnumerable. Sorry. 20 minutes. Oh, okay. Sorry. I'll slow down a bit. Okay. Whew. It scared me. All right. So what are we going to do here? Basically, we want to get rid of this return IEnumerable. Rather than having a function return some unknown thing, we're going to make it return one structure. That structure is going to be a custom struct enumerator that wraps the other enumerator and selectively returns the items that pass the where test. So the where function takes in the function. So if that func tsource bool is basically, this is a function that takes in a parameter of tsource and returns a Boolean result. If that thing returns true, we want to return the item for the person to iterate through. Otherwise, we want to skip it. So we want to build an enumerator that is a struct that does this to another enumerator. So that's what this is. And this looks much more complicated than it really is. The first couple of lines are just the enumerator it's keeping, just storage fields for the enumerator and the predicate, the constructor. The bottom four are just us passing all the other functions straight through to the enumerator. If we reset, we just want to reset that enumerator. If we want the current value, we just ask for it from that enumerator that we're wrapping, and dispose, etc. Oh, sorry. Back up. The other thing is this is taking in that enumerator. So this is a generic that takes in tsource, and the t enumerator is a generic parameter. So we're not using the interface for this, just to clarify. All of the work really is being done in move next. So basically, if you return true, it will go into the loop and it will try and use the current item. If you return false from move next, you're saying we've run out of items. So what we do is we run through the items until we find one. We call the predicate on all of them. That's our test to see if this is an item that passes our where test. If it passes that, we return true, which will cause the outer loop that's calling this to iterate that. Otherwise, we just skip until we find one that does, or we get to the end and we return false. It is so easy to write new queries. So if you want to write a select query, all you do is you have select's not a good example, but basically these things are really easy to write. You just write another enumerator that basically does the loop logic inside here. I actually wrote all of the link ones in like about 2 hours. So let's get on to the third problem, closures. Closures are one of my least favorite things in C#. So let's touch lambdas. Link extension methods are generally used in conjunction with lambdas. They are these little inline functions. So mylist.where, and it's got x equals greater than, x is greater than 1. That's a tiny method that's been defined inline. They're kind of cool. Like you could just write that as a named method outside, but you can anonymously define a method in here. The problem with lambdas is that they can capture variables from the method they're defined in. So you see in the second example, it's able to capture this greater than local member. And it's able to use it as if it's accessing it. And that seems like, oh, okay, well, clearly what's going on here, it should be like, I can only use this lambda inside this function, and it's able to somehow look back in the lower stack frame, look back in the stack and find the value of it there. No. If the lambda captures any values, the lambda's stack frame gets stored in the heap as a thing called a closure. This is almost invisible. So basically, the first example is not a closure. It does not allocate memory. The second example is a closure because it's touching something from the outer scope. It will allocate memory. This is something where you need one of those IDE plugins that tell you when you're doing this because it's hard to spot it otherwise. So we need to give the user a way to avoid having to capture values. As a comparison, if we used a static method which has no way of ever becoming a closure, we could have myMethodInt as an externally static named method, pass it into the where, and that'd be great, but then we've got no way of actually doing like, is x greater than y? We could only do it to constants, or do static things. We want to have an invariant value in this loop, but we need to have a better way to put it in. And we want to do that as a method parameter. So to do this, what we need to do is, we want a parameter on where that lets us pass in the invariant. So the value, any values we're going to use, and then they get passed to every single call of the test method. And the cool thing is you only ever need one parameter. I know a lot of people would immediately think, oh shit, I need to have the 1 parameter version, the 2 parameter version, the 3 parameter, no. Value tuples, they are my favorite toy. Value tuples are basically this min and max thing down here, open parentheses, kind of list of values or something like that. You can even name them, and then it creates a dynamic, an anonymously defined struct. So I've defined a min and max struct, and then inside the function, I then use it. I test, is x greater than or equal to inv.min, and is x less than inv.max? And yeah, this is the Lambda syntax for multi-parameters. So you put parentheses around the parameters if there's more than one. So basically, where takes in the invariant as the first parameter, and then the function is the second one. Link doesn't have these overloads, but we're rewriting links, so let's fucking do it. So we have our 2 versions of the where enumerator. The definitions are getting long, so I've started breaking them down over lines. So the first one returns a where enumerator that does not have an invariant, so that's the one we wrote before. These are the methods that that create the structures. The second one is a where enumerator, and we've added in a t invariant generic parameter as the last parameter, and then we pass in that invariant to the enumerator, the struct enumerator that we're building. And here is that struct enumerator. Again, it looks scary, but we've really only changed these lines. We've just added the invariant as a generic parameter. We store the invariant as a read-only field that's passed in the constructor, and then every time we call predicate, we pass in the invariant as the first parameter. That's it. Invariant versions of your enumerators are almost a copy-paste job. Unfortunately, you can't create a generic solution for it. So that's done, right? We've killed off the first, second, and the third problem. No, that generic inheritance, the generic method inference problems come to get us. You see, we never take t source, the item type, as a generic parameter explicitly anymore. So we need to store that generic parameter somewhere else, or people will have to specify all of these. Oops, sorry. We'll get to that in a second. We have to, if we want to create a where enumerator, these functions, someone will need to say t source, the type of the t enumerator, the t invariant, all of those manually, explicitly write those in every time they call where. That's unusable. That's an absolute nightmare. So the workaround is we change the API slightly, and we do some really heinous shit. Okay, so first of all, we are going to go and change the query syntax from mylist.getEnumerator.where, yada yada, to zinc, a static class zinc.int.begin my enumerator. And that doesn't seem like a very big change, but the entire structure of the way we do this is about to go upside down. So, no cops in the room, right? All right. So, this is how it works. Yeah, I'm going to break it down. Basically, the one to take away from this slide is that we are going to use the static class zinc more like a namespace. It will contain everything else we're doing here, and it will implicitly give us access to t-source once we're inside this thing. So any types inside here naturally have t-source. This is what I call a static type vehicle. So inside t-source, we then have a method called begin. It's a static method, and it takes in an enumerator, and it wraps that enumerator in what we call a helper structure, and just returns that helper structure. So what is this helper structure? It is a ref struct. So it is a struct that cannot have interfaces and cannot be boxed. It is generic. It takes an enumerator type as a generic parameter, so it's safe for it to use it. And it contains all of our queries. Instead of them being generic extension methods, they are now members of the helper structure. So once you've called begin, you can then call where, select, etc., etc. But all of our member methods, these query methods, now have to change. So if we did it this way, you'd have to call begin on the enumerator that they create. So instead, all of the queries now return helpers wrapping those enumerators. I have 10 minutes left. We may actually have time for questions at the end. So we're doing the same thing. This is the same where function as before. It's just returning that where enumerator wrapped in a helper of type where enumerator, t enumerator. The text gets very long, but it's not complicated. We could go and nest all our enumerators inside the helper type, but it's a very bad idea. This is just kind of a cautionary thing. Every time you use a generic type, it builds out the code for everything that's in there. If we could avoid having our enumerator types be generic types by putting them inside the helper, but then every time we use a type of helper with a type of enumerator, it would create all of the query enumerators even if we weren't using it. It would create a lot of extra sort of compiler bloat. So rather than that, we just make them generic. We have them live inside the sort of static class namespace to keep them a bit simpler. But yeah, just be careful of that. The size of your generic classes can bloat your compile times a bit. All right, so how does the help them thing work? Well, it's a ref struct. It's not allowed to have any interfaces. So how do we use it? Well, remember how for each and other things allow us to duck type the get enumerator function? We could just slap get enumerator in here and pass out the enumerator that it's wrapping. And then we can just for each the query. Like the result of the query is going to be the last helper that we created. So in this case, this query is just going to begin and then it creates a where one, but we could stack multiple wheres. We could put where, select, find first, etc. As if it returns a helper, we can iterate through that as if it was lists. The other nice thing is because these are structs and the helper stores this as a read-only struct, or rather it's returning a copy of the enumerator for this, you can safely rerun this query because struct enumerators will keep their state. So that's a nice extra bonus. You can't do that with LINQ. So we've covered most of the stuff to do this. The final thing is that syntax of calling zinc int begin, like explicitly saying what's in your list sucks. So we want to say, have a API where we go mylist.zinc where, and then just continue like that. So get rid of the explicit zinc static call to begin. Unfortunately, there's no really good way to do this. Remember, if we created an extension method that accessed the container types as their interfaces, we'd run into the problem from the first part of the talk where we'd be getting the wrong version of get enumerator. So we need to go and make explicit extension methods for each container type. So we make one of list so that we can get the list enumerator. We make one of the hash set so we can get the hash set enumerator. So we build all the ones for our own types and then expect the end user to go and add their own. Fortunately, they're really simple. There's a bit of extra compile fluff here, but autocomplete will just fill this shit out for you. Basically, all it's doing is it's just calling begin, like zinc.begin myContainerType.getEnumerator, and it's just returning that. So you make these, they take 2 seconds. You just replace lists with what you want. The only edge case that I found is arrays, where you've got to have build your own custom enumerator for that, but that's in the source code, and plus we've covered how to do custom enumerators, so that's homework. And holy shit, that's it. We are actually under time. I expected that we would have to take questions out in the hall. I do appreciate this is a lot. So here is where the slides are. Here is a package that does all the enum stuff. Here is the complete version of Zinc. Please feel free to tear them apart. Let me know if you find any problems. These are actually road tested in games though. And yeah, any Q&A? Do we have time for Q&A? Yeah. Okay, cool. So I'll pass this on.
Those are pretty malleable if you want to move them.
Yes.
Hey, firstly, fantastic talk. My brain is melting.
Yes.
I was just going to ask, you mentioned some plugins about boxing. Do you have any recommendations in that space? And the other thing is also, this looks like a lot of boilerplate work that's recreating existing functionality. Is there any packages or sort of shortcuts of pre-written versions that are kind of a bit more out-of-the-box usable that's
so
worth looking into?
These two packages here can be installed directly in Unity as UPM from the GitHub, and they do that. They do the enums thing, they do the link replacement out of the box. They're not the best documented things, but they are road tested. So yes, on those. As far as the first one, the first part of the talk is really how do you write methods to do, like, enumerate any type of collection. You really need to do that in your own local space, like local where you need to do them. Sorry, what was the first part of your question?
The first part was the plugin around detecting boxing and things like that.
So if you're using Writer, in the plugins thing, if you just search for heap allocations, you'll find it. With Visual Studio, I think there are several options. The one that I used was ReSharper, had support for one, but I'm sure that there are several others in the Visual Studio kind of plugin marketplace. If you look for heap allocation viewer or boxing, you'll find something in one of those two keyword searches.
Fantastic, thank you.
Hey, once again, excellent talk. Two things I wanted to go over, which were more just like notes, I guess. If memory serves, Unity's still in C#6, right?
No, they're up to C#8.
Oh, excellent. Okay,
So
well,
that's why we're able to use like all the value tuples and all of this stuff.
true. Well, look forward to C#9 because that lets you declare static lambdas, which stops you from accidentally creating closures.
Thank fuck.
The other one was in terms of like the API stuff. I'm pretty sure you can declare argument types for your arguments in lambdas, which I think sort of propagates backwards. So if you declare it in the lambda, your other arguments that are incorporated into it will sort of pick up that typing information as well. Now for my actual question. So if memory serves, returning structs sort of, doesn't that return the entire value of the structure type depending on how big it is?
Yes, that is one of the problems of Zinc. One of the ways that I get around this as much as I can is that in Zinc I don't return as many of the values. I prefer to use a final query type called to, which will write the values to a collection. Again, that is writing by value. It's actually really hard to write a return by reference approach to this. I've done some stuff with it, kind of on the same vein. I have used the method, explicit argument types inside the lambdas. It's an annoying syntax to use comparatively, but if you want to have like in types, like in parameter types for these queries, which I experimented with, you have to use that because it messes with the generic inference. It's okay, but at the same time, Zinc is intended as a replacement for link code. It's supposed to be as close as possible, so it's a bit outside the scope of what I was trying to build with that thing. I definitely agree that if you wanted to have a as performant as possible thing, that's a really good option. But yeah, be aware that all of the Zinc functions do a lot of struct copy by value, sometimes deliberately, sometimes just not able to avoid it. Like it was a case of either the API had to drastically change and become more difficult to use and less compatible with Link, or I could keep it close to Link and it would be an easy one-to-one replacement. That was really my goal.
Thank you.
All right, that should do it. Do you want to take more questions outside?
Oh yeah, cool.
Thank you very much.